Good morning and welcome back, everyone, to the fourth day of the first week of the summer school. Without any further ado, let's have Thomas start on his next lecture on the mathematical formulations of numerical relativity.
Thank you. Good morning, everybody, and welcome back. So let's just retrace what we've done so far this week. Right, we started Monday by just laying out gravitational theories. Then Tuesday and Wednesday, yesterday, we basically talked about the 3+1 decompositions. We basically practiced doing that in the context of E&M, electromagnetism, but then applied that to general relativity. And by the end of the day, we derived basically the 3+1 decomposition of the GR, of general relativity. And the equations that we arrived at were the so-called ADM equations for Arun, Deser, and Misner. I just learned earlier this morning that Charlie Misner passed away just the other day. So it's very sad to learn that. Okay? Stan Deser also passed away just a few months ago. So basically, this is very sad that these true giants of our field are no longer with us. So actually, I thought it was well worth mentioning that. So what we've seen, though, is that when we perform a 3+1 decomposition of the field equations, we end up with a set of constraint equations and a set of evolution equations. Today, we'll talk about how we can solve the constraint equations. We'll develop some strategies for doing that. Tomorrow, we'll talk about what we need to do to solve the evolution equations, right? So here's our chapter 3, solving the constraint equations. Let's remember that in GR, we have two constraints. One is the Hamiltonian constraint, the trace, the three-dimensional Ricci scalar, plus the trace of the extrinsic curvature squared, minus Kij equals 16 pi times the energy density as measured by a normal observer. And the other constraint is the momentum constraint, which is basically the divergence of the extrinsic curvature minus gamma ij times the trace of the extrinsic curvature equals 8 pi times the momentum density as observed by a normal observer. Let's compare that, guess what, with E&M. In E&M, we also had a constraint equation. In that case, it was just Gauss's law. The divergence of E equals 4 pi rho. Okay? And I would like to make the analogy with a momentum constraint. In both cases, we have a divergence of a variable, which actually we consider the time derivative of our fundamental variable. In the E&M case, it was the time derivative of the vector potential A. Here, it is the time derivative of the spatial metric gamma ij. All right? Now, in the E&M case, we have three unknowns, the three components of E. Okay, so there are three unknowns. But you notice that we only have one equation, one scalar equation. So it's clear that our fields, the three fields, are underdetermined. The constraints do not completely determine the fields. Okay, so it's underdetermined. Clearly, we cannot solve for all the three components of the electric field by solving the constraint alone. Okay? So what that means is that we have to choose some of these and then choose two of them and solve for the third. Okay? Now, that's not totally counterintuitive. In fact, that makes perfect sense. Because imagine I held a charge here, and if this is a static charge, then I can compute the electric field caused by the static charge everywhere. That is the Coulomb field. Okay, we know how to do that, and that will, of course, solve the constraint. Okay, so I could get that just from the constraint alone. However, in addition to any such static field, we could also have an electromagnetic wave traveling through our space. There's no way that I could determine the electromagnetic wave from the constraint equations alone, because knowing about the electromagnetic wave would require the history of our space. We would need to know where the wave came from. So what that means is, basically the static fields, what we call the Coulombic fields, we can determine from the constraint, whereas the dynamical fields we cannot determine from the constraint. So it makes sense that we cannot determine everything from the constraints. Okay? In general, sometimes people also refer to longitudinal fields, which are the same as the Coulombic fields, those that can be determined from the constraints, versus transfer fields, which are the dynamical ones, which cannot be determined. Okay, but the bottom line is we cannot determine all the fields. We need to make a choice as to which ones we want to guess or determine or fix by hand, and which ones we want to solve for. Okay, so basically, the name of the game here is that we have to choose two variables. Okay. And we generally refer to those as the freely specifiable variables. So freely specifiable. Okay. Or I will abbreviate it as FSV, freely specifiable variables. And then once we've chosen two of the variables, we can use the constraint to solve for the third. So we then compute the third, and we refer to that variable as the constraint variable. Okay, or variables if there's more than one. I'll abbreviate that as CV. Okay. Of course, now you should ask, okay, that's great, but tell me which one is which? Okay, and of course, there's nobody telling us, there's no rule for saying, okay, which two of these you choose and which one you solve for. So again, there is a choice involved. We have to first make a choice, which ones do we want to specify by hand and which ones do we want to solve for. That's what we refer to as choosing a decomposition of the constraint equations. Okay, so here's the general procedure. Okay. So we start by choosing what we refer to as the decomposition, which should not be confused with the 3+1 decomposition that we talked about the last 2 days. This is now a decomposition of the constraint equations. And what we mean by that is that we separate the freely specifiable variables from the constraint variables. Okay. Then, in the next step, we make actual choices for the freely specifiable variables. And finally, having made those choices for the freely specifiable variables, we solve the constraint for the constraint variables. So finally, we solve the constraints for the constraint variables. Okay, so let's think, about an example. How could we imagine doing that in ENM? Okay. One option would be to say, well, guess what? Let's say we have this in Cartesian coordinates. Then the E field has 3 components, EX, EY, EZ. How about I choose EX and EY, and then I can solve the equations for EZ. Okay. So basically one option would be, I could choose EX and EY. Okay. And then solve for EZ. Okay. I'm not suggesting at all that this is a good way of doing that. Okay? In fact, this already sounds kind of weird. I mean, why would you introduce kind of an asymmetry between these coordinates? So this seems very awkward. Okay, just saying, if you really wanted, you could do this, but I don't recommend it. Okay, it just would be one way of doing that. Here would be one alternative. Okay, if we wanted to not introduce this weird basic asymmetry between these 3 coordinates, what I could maybe do, I could write EI, my solution, as some overall scale times maybe a unit vector by which I determine just the direction of the E field. Okay, so maybe I say, okay, at this point. I want the E field to point in that direction. And then I let the constraint tell me how large the E field is going to be at that point. I ask it to tell me about the magnitude of the E field at that point. So basically I could factor out an overall scale factor and then just solve for the scale everywhere. That would be a different way of doing that. Okay, so maybe we would then solve for a scale. For a scale or the magnitude, okay? And here we would basically choose maybe the direction of the E field, or a more fancy name for it is maybe we would choose the so-called background fields. All right. In fact, we'll do something in GR, and that's why I'm suggesting that here. Okay, so now let's see, how can we do this? How can we do something similar to solve the constraint equations? So what that involves is actually doing something similar. We'll write our variables as the product of a factor times some other variables, okay? So which is always allowed. I'm always allowed to write an unknown as the product of two unknowns, okay? You might ask, what is that good for? Why would you want to have more unknowns? But that we'll find out what it's good for. All right, so the fancy name for doing that is we use a so-called conformal transformation. So let's talk about conformal transformations. So in GR, what we'll do is we will write the spatial metric, which is our unknown, or one of our unknowns, gamma ij. Let me write that as a factor times some other metric. And the other metric I write as gamma bar ij, and I'll refer to that as the conformally related metric. And this factor, I'll call the conformal factor, okay? But actually, for convenience, just because later on our expressions will become easier, we will not multiply with the factor itself. Instead, we will multiply with psi to the fourth, okay? And so again, this psi is the conformal factor. Actually, you've already seen examples of this conformal factor in the tutorials, for the Schwarzschild metric, right? So we've seen those factors. I'll also let you know that basically this whole formalism was introduced by Lishnerovitz in 1944, and then Jimmy York really developed this in great detail in 1971 and in later years. Okay? Now, we can think of this again as just as a mathematical trick. We write our unknown as a product of two unknowns, but we can also think of this new metric, this conformally related metric, as defining a whole new conformal space. And then we can use all our tools, okay, for differential geometry that we've applied to the space-time metric and then to the spatial metric. We can apply those exact same tools also to the conformally related space and metric. Okay, so we could now go ahead, for example, because we had so much fun computing Christoffel symbols for the space-time metric and the spatial metric, we could now go ahead and compute Christoffel symbols for this conformally related metric. Okay, so for example, my point is we can define all our objects and tools from differential geometry now in terms of this conformally related metric. So we define geometric quantities associated with this conformally related metric. So for example, we could define a covariant derivative.
Thomas?
Yeah.
I just had a question.
Yeah, that's cool. Sure, go ahead.
Is it a direction composed of three things? So we are essentially having four instead of three.
Okay, in this you mean? Or?
In the electric field, for example.
In here?
Yeah.
Okay, so basically, so here I also introduced, I wrote my unknowns, EI, as a product of phi and the E bars. Now, basically, in this case, what I would do, I would choose all three of the EI bars. Okay. So, for example, one way of doing that is I would say at each point in space, I would define, I want to give the direction of the E field. So I would basically define a basis, a unit vector at that point. So that means basically that is to determine that unit vector, I would specify three quantities, right? Yeah. It's a vector of magnitude 1. And once I've specified these three, then I can solve the constraint to solve for the phi.
So the very fact that is of magnitude 1 constraints from 3 to 2 in the direction wise.
So I think, if I'm understanding your question right, it is basically, I mean, there's always, this does not completely determine the E fields by itself, because this does not tell me about the magnitude of the E field. So there's basically one quantity left that I still need to determine, and I determine that by solving the constraint equation. Right? What I suggest is this is kind of a silly example. I was hoping it was useful, but now I realize maybe for you it was more confusing than useful. What I suggest is let's keep going with this, and then I think we see what this is good for, okay? And then actually, if not, we can go back and discuss what is going on here, okay? So basically, if we keep with this program, we can define the covariant derivative associated with this gamma ij bar. And we would do that exactly the same way as we did it before, i.e., for example, for the covariant derivative of a vector, we would write it as the partial derivative of the vector components plus Christoffel symbols, which I now call gamma bar jki. And these gamma bars I now compute from the gamma ij bars in exactly the same way as you're used to it from the other from a different metric. Okay, so we compute this from gamma bar ij. All right. So this gives us the Christoffel symbols. Then we could compute the Riemann tensor in the same way. We could compute the Ricci tensor and all of those. For example, the Ricci tensor R bar ij, we would write as 1/2, and then there's the gamma bar KL, and then partial derivatives, partial K, partial L, gamma bar ij, and all the other mixed derivatives, and then plus terms that are of order gamma bar squared. Okay. Now, actually, what you notice is we need not only the metric, the conformally related metric, we also need it's the inverse metric. Okay. So, and of course, we also need that in the gamma jkls. We want the inverse metric of gamma bar ij to be defined in such a way that basically the contraction of the inverse metric with the metric gives us the Kronecker delta. And we get that if we write gamma ij upstairs as psi to the -4 gamma bar ij. Okay? Because in that case, we get gamma ik gamma kj equals delta ij. All right. Now, because gamma bar is basically given by a product of gamma ij and some power of the conformal factor, we could compute these gamma bars from basically the products of gamma and the conformal factor. In each derivative that appears in the Christoffel symbols, we just use the product rule. That means for each derivative, we now get two terms. One term will just be the derivatives of the metric itself, which we already know gives us the unbarred, the spatial physical conformal Christoffel symbols. So clearly, these gamma bars must be the unbarred gammas plus some corrections, which are related to derivatives of the conformal factor. So in fact, basically, I'll ask you to show in the tutorial that, for example, the gamma ijk is the same as gamma ijk bar plus terms that are derivatives of the conformal factor. So for example, there would be a delta ij partial k times the log partial k of the logarithm of psi, and then permutations that you get from the other derivatives. Okay, so this is something you can do in the tutorial. You can check that and verify that. But it's clear where that comes from, right? Because these Christoffel symbols are just derivatives of the metric. When we write one metric, as a conformal factor and another metric, then we use the product rule, and we get those two sets of numbers. Make sense? Okay. Now, guess what? We can do the same thing for the Ricci tensor. Okay, what would we expect for the Ricci tensor? Well, something similar, because the Ricci tensor is also defined in terms of derivatives of the metric. So now for the metric, you insert those products of the conformal factor and the conformally related metric. That gets pretty messy pretty quickly, okay? But you can imagine that basically you again get the unbarred Ricci tensor plus correction terms, okay? And you could check that for yourself if you don't have anything better to do, okay? Then we take traces of that, because by the end of the day, we need the Ricci scalar, right? Because we are interested in the Ricci scalar because it appears right there. And it turns out, if we follow this program and take all these derivatives and work out what it is, what we find by the end of the day or the end of the week or whatever it might be, okay, is psi to the -4 r bar -8 psi to the -5 d bar squared psi, where this d is now the conformally related Laplace operator, which is the same as gamma ij, d bar I, d bar j acting on psi. Okay? So again, basically, I don't expect that you see, oh yes, that must be right. But you probably see that it must be something like that, because the only term, basically, this involves second derivatives. So the only term that you would get by the end of the day are second derivatives of the conformal factor, and that's what is hidden in there. All good? Make sense? Okay. So now what can we do with that? Well, we will insert this into the Hamiltonian constraint. So let's make room for that. So basically, I'll insert that R into this R here. In fact, no, I'll write it. I was wondering whether I can recycle that equation, but maybe it makes sense to start over. So then, the Hamiltonian constraint becomes d bar squared acting on psi minus psi divided by 8 r bar plus psi to the 5th divided by 8 times kij minus k squared equals minus 2 pi psi to the 5th times rho. Okay? You're with me? So now I think we're coming back, kind of the extension of your question, right? You were asking, okay, what is this good for? No, essentially that equation is the equivalent of what we would get if we inserted this into the equation that I just erased here, the Gauss's equation. Essentially, Gauss's equation would turn into an equation for phi, which we can solve assuming that we had made choices for all the E bars, right? So now, basically the same is true here. What we will now do is we'll make choices for all the gamma ij bars. We will say, we will solve the Hamiltonian constraint by making a choice for the conformal geometry. And having made that choice, we can then solve for the conformal factor. Okay, so let me write that down. So we now choose I'm sorry, we can choose gamma bar ij What that means in our earlier language is that we declare our gamma ij bars to be our freely specifiable variables. By doing that, we've chosen a decomposition, right? Yes?
We were transforming the extrinsic curvature according like.
Oh, okay. So we haven't done anything with the extrinsic curvature yet, right? So basically, I've left these terms untouched. Those are the same as before. Okay. So are you asking, are we going to the conformal transformation of the extrinsic curvature too? Absolutely, we will do that. Okay, but you're a few steps ahead. Okay, so hold your thought. We'll come back to that in 10 minutes or so. Okay. For now, we'll just basically, so far we've only worked on these spatial metric, and we've used a conformal decomposition or the conformal transformation of the spatial metric. Okay, so basically, what we'll do now is we'll consider the conformally related metric, our freely specifiable variables, okay? Meaning we will make a choice for that. Where will that enter? It will enter, I mean, we don't see a gamma ij bar in here, but actually, can anybody tell me where are they hidden in this equation? Why do I need to know about gamma ij bar? They are hidden where? They're hidden in R bar. And also, of course, in the covariant derivative here. Okay, so that's where they enter. That's where they're hidden, right? But once we've chosen those, and once we've chosen the extrinsic curvature, okay, if we knew the extrinsic curvature, and we've made choices for gamma ij bar, then we could solve this equation for psi. Okay, and that will be a nice way of solving the constraint, because it's now an elliptic equation for psi. This is an equation that we can solve pretty easily. Right? So we could then solve for the conformal factor psi, which is now our constraint variable. Let's do an example. Okay, let's find some simple solutions, which I refer to as elementary solutions to this. Okay. Okay, so how can we make this simple? First, let's talk about vacuum. Let's throw out any matter. Okay, so we only talk about vacuum fields. Okay, so if we're talking about vacuum, then rho is 0, and the charge densities, current densities J that appear in the momentum constraint are also 0. Okay. Now, let me also consider what we call a moment of time symmetry. Okay. So we're assuming there exists an instant of time about which the evolution is symmetric. That means that the time derivatives at that moment must be 0. And we'll translate that into meaning that the extrinsic curvature at that moment must be 0. Okay, so we'll assume a moment of time symmetry. And basically what I mean by that is that Kij is 0. Okay. Now I erased, unfortunately, the momentum constraint, but look up the momentum constraint in your notes, and you'll see that if we have Kij equals 0 and J equals 0, then the momentum constraint is satisfied identically. Okay, 0 equals 0. Nothing left to be done there. Okay, so basically the momentum constraint is solved analytically. Okay. What we still need to solve or to make a choice for is the conformally related metric. And in order to keep this simple, we will choose the conformally related metric to be flat. Yes, go ahead. So, but it's time symmetry means that I'm assuming that I have a moment of time about which basically if I integrated this forward in time, I would get the same thing as if I integrated backwards. Okay. Oh, remember that Kij is basically the time derivative of the spatial metric, right? So basically, what I mean by time symmetric is that the time derivative of the metric must be 0. And because the extrinsic curvature is basically the time derivative of the spatial metric, that means that basically the extrinsic curvature must be 0 at this moment. So I'll set that to 0. Okay? Good. Okay, so what we'll do is we will choose the conformally related metric to be the flat metric, which means that what we refer to that is we call this geometry be conformally flat. Or the noun is conformal flatness. Okay, so what we mean is that gamma ij equals eta ij, the flat metric. Okay? That is our choice. It was our freedom to specify the freely specifiable variable, and we made this choice that it's now flat. Okay? If that is true, what does that mean for the Ricci scalar? It is, can I hear that loud and clear? 0. I agree, right? The R bar is 0. Okay. How about the derivative operators? They become what kind of covariant derivative operators? Those of flat spacetime, right? So they're just flat space covariant derivatives. In Cartesian coordinates, they're just partial derivatives, okay? So these become DI. The DIs are flat covariant derivatives, okay? And basically, in particular, this operator now becomes your garden variety Laplace operator. You could express it in Cartesian coordinates or spherical polar coordinates, I don't care, but it's just, you know, the covariant derivative, the Laplace operator that you would look up in any textbook on E&M or whatever, okay? So that means that the Hamiltonian constraint reduces to, let's see, this term is gone, these terms are gone, this term is gone, we only have this one left over. Okay, that is lovely, right? So basically, we now have the flat Laplace operator acting on psi equals 0. That's it, okay? So let me call this equation 1. And remember that this d squared, this is not a flat Laplace operator. Okay. Let me write down this Laplace operator in spherical coordinates, spherical polar coordinates. Okay. Actually, you know what? What I meant, let's erase this. What I meant is spherical symmetry even. Let's specialize to spherical symmetry. In spherical symmetry, this actually we only have now one derivative. So these are d's. 1 over r squared ddr of r squared d psi dr equals 0. Okay. And probably you have all seen how to solve that equation. Okay? So we can write down solutions to this equation. Actually, do you want to report to me what are the solutions to this? So we could solve it. Clearly, I can multiply it with r squared. Then this will still be 0. Then I can integrate once. That means that this combination must be a constant, right? And then I could divide by r squared, integrate that once, get a second constant of integration. And what we see then is that psi must be some constant a plus a second constant divided by r, okay? And of course, you could also insert this into this and just verify that you get 0 identically, okay? Now, basically, now we have to choose these two constants, okay? We don't know yet what those are. But we could make a choice. We could say, well, you know, asymptotically, we want to recover actually Minkowski spacetime. So we want the spatial metric to go just to the flat metric. So that means we want the conformal factor to go to 1 as we go to infinity. That means this constant a should be 1. Okay, so basically we can choose A equals 1, so that psi goes to 1 as r goes to infinity. Okay. We could also basically evaluate what is the total energy in this space-time. We could go to large distances, measure basically the mass in the space-time, and then we would notice that the mass is related to this constant b, which means we could also express this b in terms of the mass. And what we identify then is that b is the same as m half. So if I insert this, we get psi equals 1 plus m divided by 2r. Have you ever seen that? Isn't that nice that that was on the tutorial on Monday? That is lovely, right? Because that's our old friend now. That is exactly the conformal factor that you got on Monday when you transformed the Schwarzschild metric to the isotropic coordinates. So this is actually an old friend of ours, okay? So this is the conformal factor that we get from this, okay? Now you could ask the question, boy, did I have to sit through hours and hours of lectures just to recover something that I already knew on Monday? Are we wasting our time here? Okay. Well, of course, this is just one particular example, but notice something really lovely, okay? See, it is true that we've seen this before, but this is now basically the solution to the Hamiltonian constraint under these particular assumptions. Okay? But also notice that under these assumptions, the Hamiltonian constraint is a linear equation. If it's a linear equation, then a superposition of solutions is also a solution. I can use the superposition principle. So in fact, we can now generalize the simple solution to construct initial data describing not one black hole, but multiple black holes. For example, if we wanted to compute the head-on collision of two black holes, we could construct the initial data by just adding two of these terms. That would be a solution to the constraint equations, as we see, because it's linear. Okay, and as long as we're still in time symmetry, all of the assumptions still hold. Okay, so that is a beautiful thing. Now we know exactly how to construct initial data for multiple black holes, as many black holes, in fact, as you want, okay? So what we note, okay, equation 1, this one, is linear. Okay, so that means we use superposition. To find solutions for multiple black holes. So, actually, you know what? Let me erase this. So actually, let me write it maybe here. So psi equals 1 plus. And now we could add over multiple terms. Let's say for capital N black holes, we would have an Mn divided by 1, 2 divided 2Rn, where Rn would now measure the coordinate distance, or the coordinate position, the coordinate distance from each one of these black holes. Okay? These are the so-called Brill-Lindquist solutions. Solutions, okay, which go back to 1963. Okay. Now, let's just make one point clear. Basically, when we have the solution for just one black hole, we also got that by transforming from the Schwarzschild solution, which you did on Monday. The Schwarzschild solution is very special because it gives you, it's a static solution, meaning that solution is valid at all times, okay? And likewise, if we just use this as our basic, as a solution to the constraint equations, if we evolve this with the evolution equation by itself, with appropriate coordinates, we would also find solutions that are static and independent of time so that the solutions would hold at all times. That is not true for this solution, okay? That's why you don't find analytical solutions for binary black holes in textbooks, for example, because they don't exist, okay? We can write down these solutions to the constraint equations, meaning these give us, this is a valid solution at t equals 0, okay? But not after that. Why is that? Because if we now evolve these, then, for example, extrinsic curvature would no longer be 0, things would be messier, okay? These, in other words, these are valid only at our initial moment of time symmetry. These are only the initial data, okay? All right? Yes? Sorry, is that the? Okay, so you're asking what is this mass here? Is that right? Yes, I was non-committal about that. I didn't say anything about that, right? And you know what? I was non-committal on purpose because that's a little bit messy. So what exactly is the physical interpretation of these M's, okay? We use them to parameterize the mass of each one of the black holes. But if we went local, basically the total mass of the space-time also, also involves the binding energy between these black holes. So basically these numbers, they're basically numbers that parameterize the mass. But if we actually measure the individual masses by looking at quasi-local properties of isolated horizons or the dynamical horizons, they would be slightly different numbers because there's the interaction energies that also play a role. So very good question, okay? Yeah, I swept that under the rug, but you pulled it right out. Okay. Yeah. Anything else? Okay, now you asked about the extrinsic curvature. So what we should do next is say, basically, great. So now we have some idea how to solve the momentum constraint. But you know, what if the extrinsic curvature is actually not 0? What if we don't want to specialize to moment of time symmetry? How do we deal with the extrinsic curvature? So let's talk about that. So maybe I'll start over there again. Let me erase this. Okay, so now we'll consider the momentum constraint, and we'll use a similar approach as we did for the Hamiltonian constraint. I will also use a conformal transformation of the extrinsic curvature, but it goes a little bit differently. So let's talk about conformal decomposition. Of the extrinsic curvature. Right? So let me start by writing the extrinsic curvature as a sum of two tensors. One is the traceless part of the extrinsic curvature, which I'll call Aij. And then I add to that back in the trace by adding 1/3 gamma ij times k. Okay, so k is now, this is the trace of the extrinsic curvature, which we also refer to as the mean curvature. Okay, so this is gamma ij kij, and this aij is traceless, meaning that gamma ij aij equals 0, okay? And you can verify that basically, if I take the trace on this side, basically taking the trace of gamma ij gives me a factor of 3, that cancels 1, 3, so that this is the correct trace and it all works out. So this is one way to split the extrinsic curvature into one part that is traceless and one part that's only the trace. Now we look at these individual parts, the mean curvature and the traceless part, and we can conformally transform them individually. Okay. It turns out there's no advantage really to doing a conformal transformation of the mean curvature by itself, so we'll leave that alone. But there is an advantage in considering a conformal transformation of the extrinsic curvature. And the reason for that is the divergence term that appears in the momentum constraint. Okay? So what we'll do is we'll consider a rescaling of Aij. And I'll start with the upper indices because remember in the momentum constraint, the way we wrote it down, we also had the upper indices. Okay? And basically what I will propose is that we write Aij as psi to the minus 10 times a new covariant, conformally rescaled version of Aij, which I call Aij bar. Okay. Why this minus 10? Because it turns out precisely for this power being minus 10, you can show that the divergence of Aij will be psi to the minus 10 times the conformally related divergence of Aij bar. Okay. I'll ask you to look at that on the tutorial so you can check this for yourself. Okay, so there's a coincidence basically. If you basically use this particular exponent, then in the divergence, the psi to the 10 comes right out of the divergence, and that makes our lives easier. Okay, what's not to like? All right. Also, we have to look at these contractions Kij, Kij that appear in the Hamiltonian constraint. And so we also have Aij equals, what was Aij lower? That is the same as Ik gamma JL times AKL. Okay. I'm sorry, let's lower the indices first. That's what I meant. Now let me insert the conformally rescaling for the spatial metric and the conformally rescaling. Goodness, I'm completely messing up here. Why I messed, we don't need this anymore, do we? Huh. Okay, being disorganized. You know what, let's make this nice, right? So we start over here. So let me lower the indices on the Aij. So we have Aij equals gamma Ik gamma JL times AKL. Okay. Now I will insert the conformal rescaling for both the gammas and the AKL. The gammas both have a factor of psi to the 4. So I pick up a factor of psi to the 8 times gamma bar Ik, gamma bar JL. The AKI upstairs has a psi to the minus 10 times A bar KL. So that means I now get a factor of psi to the minus 2 gamma bar Ij if I define gamma bar Ij with the lower indices as the upper one with the indices lowered by the conformal metric, which makes sense. Okay, so now we see that basically lower indices basically transform like this. Okay, and then we can look at this contraction of the extrinsic curvature Kij, Kij. We can insert first basically this composition into traceless part and the trace. Then we insert the conformal rescaling for both A and gamma. And if you do this, you can check for yourself. You will get psi to the minus 12 times gamma bar Ij, gamma bar Ij plus 1/3 K squared. Okay. Now you might worry, but wait, where did all the cross terms go? But the cross terms consist of contracting gamma Ij with Aij, and that gives us what? 0, because Aij is traceless. Okay, so that goes; those terms all go away. That's why this cleans up pretty nicely. Okay. So then we can insert all of this into the constraint equations, and then we get this following. Then we have the Hamiltonian constraint. Becomes nabla squared psi minus psi 8 r bar, which we had before, right? This is, yeah, Laplace operator, conformally related Laplace operator, plus, now we have a psi to the minus 7, which we get from psi to the 5th times psi to the minus 12, okay? Divided by 8. Aij minus 1/12, oops, times psi to the 5k, k squared, strictly speaking, equals minus 2 pi psi to the 5th rho, okay? So that is now the Hamiltonian constraint. And the momentum constraint is the following. Because of this scaling, this becomes quite simple. Okay, so we immediately get an equation for the conformal divergence of Aij. And now we get an extra term from the second term in the equation, which is 2/3 psi to the 6th times gamma ij bar djk equals 8 pi times psi to the 10 ji. Okay, so those are now our two constraint equations. Right? Okay, now we have to talk about how do we solve those? Okay, or can we construct any, solutions like, and can we find analytical solutions to those? Well, not completely, but we can, yes. In particular, we can in fact find analytical solutions to the momentum constraint, namely solutions that describe black holes, either basically black holes with momentum, a linear momentum, or an angular momentum. Okay. So let me show you how we can do this. So let's talk about black hole solutions. To the momentum constraints. So if we want to construct black hole solutions, we're considering vacuum solutions. That means J is 0. So the right-hand side is already gone. Right? So we choose vacuum, meaning that Ji equals 0. Okay. Now we will also choose this mean curvature to be, we can make a choice for the mean curvature. Okay. And then that will allow us to solve for the remaining terms of the extended curve, which is the traceless part. Okay. So let's choose K to be 0. And there's a name for that choice that is called maximal slicing. Okay, so we'll assume maximal slicing. By which we mean K equals 0. All right? In that case, the momentum constraint will reduce to just this one term. Okay, so basically then, the momentum constraint will be just one term, namely nabla j, a bar rj equals 0. Okay. Now let's make two observations. One is, this is again a linear equation, okay, which is remarkable, right? Even though, I mean, clearly Einstein's equations are not linear, but basically in this decomposition, basically the way we've chosen our freely specifiable variables, this reduces to a linear equation. So that is nice because we again, once we have any solutions, we know that we can again use the superposition principle to create multiple solutions. Okay? The other thing that you notice is that this, by having chosen K equals 0 and J equals 0, the appearances of psi disappeared. So this equation is now independent of the conformal factor, which is great because that means we can solve this equation by itself without simultaneously solving the Hamiltonian constraint for psi. Okay, so basically there's really two beautiful things. A, it's a linear equation. B, it decouples from the Hamiltonian constraint because we can solve it without knowledge of the conformal factor. Okay, so let's observe this is linear. And it decouples from the Hamiltonian constraint. Now also notice that this equation truly is now very similar to the Gauss's equation in E&M. Where for vacuum solutions, we would solve the divergence of E equals 0, right? And so before we actually go further, let's talk about just a little bit, how would we actually solve this equation? I made these hokey suggestions earlier that, oh, maybe you choose EX and EY, then solve for EZ. Or I made this hokey suggestion, why don't we choose the direction of the E field and solve for the scale? But actually, in an E&M course, how do you actually solve this equation? Sorry? You know, I'm sorry, I still cannot hear you. Yeah. Yeah. Now you're giving up? Oh, I'm sorry. Well, what do you do with the E? We can write the E field as what? A gradient of a potential. And then we insert the potential into that, okay? And then we have basically the Laplace equation. We solve the Laplace equation. Why are we allowed to write E as the gradient of a potential? Why is that? That's right. By the way, did we make an assumption? We did, because you, by saying, oh, let's write it as a gradient of potential, you first said, actually you didn't say it, that's the problem. Okay, no, I'm kidding, of course. You made the assumption that E is irrotational, right? So basically what you are suggesting is only true of E is irrotational. So in general, we could say, maybe we could remember Helmholtz theorem, which tells us that if I have a vector, I can always write the vector as a sum of two vectors, okay? One has zero curl, it's irrotational. One has zero divergence, okay? Now you notice the curl part, okay, has zero divergence. Any contribution that has zero divergence will automatically drop out of this equation because here we are taking the divergence. That means that the curl part, the term that has zero divergence is unconstrained. Those are the transverse parts, okay? The other part is the part that has zero curl. And then what you said, you invoked this beautiful result that if there's a vector field that is irrotational, has zero curl, then we can write it as the gradient of a scalar. And by inserting this, we get a scalar equation and actually an equation with beautiful mathematical properties, namely it's an elliptic equation, it's just a Laplace equation for this particular scale. That's how we solve this. Okay? And then we could solve this equation. Sometimes we can write down analytical solutions and all is fine and well. Make sense? It turns out that we can do the same thing for this equation. So we could go through several steps, okay? And we could split this tensor now. Everything is now one rank higher, not unlike in the decomposition that we talked about the last couple of days, okay? But there's an important result that tells you that I can also split this tensor in one part that has zero divergence, okay? That part will automatically drop out of the constraint equation because once we take the divergence, it's gone, okay? And the other part, the remaining part, we can again write in terms of derivatives of some other thing, but because it's now one rank higher, it's no longer the gradient of a scalar function, it is now basically derivatives of a vector, okay? So we could write this down formally. we could write those terms, the constraint terms, therefore, in terms of this vector. We would insert that into this equation, and we could then basically, we would get kind of a vector Laplace equation for this particular vector, which we could then solve actually analytically. Okay? Instead of going through all of those steps, okay, because life is short, and so is this lecture, okay, basically, I will just give you the result. In fact, I give you two results. Okay? I'll give you one result for spinning black holes that carry angular momentum, and one result that describes boosted black holes, by which I mean black holes that carry linear momentum. Okay, so basically, but that was the outline. That's how you derive this. I will give you the solutions, and you can verify, taking the solutions, you can actually insert them into the constraint, and you can check for yourself that these are valid solutions. Okay. So let me write those down. Okay, so we do this, before we do this, we again simplify the problem by assuming conformal flatness, so that these operators again become the flat covariant derivatives. In Cartesian coordinates, they would just be partial derivatives. Okay, so we assume conformal flatness. I.e. gamma ij bar equals eta ij. Okay, and then analytical solutions are given by, okay, there are two. So here's the first one. A ij bar equals 6 divided by r cubed, where this gives us the extrinsic curvature anywhere in space. And the r measures the coordinate distance from the point that I'm evaluating the extrinsic curvature at to where the black hole is. Okay, so it's a coordinate distance from the black hole times an Li epsilon bar j k kl times j k ll. And now we need to symmetrize over the I and j's. I need to tell you what the L is. The L is basically the unit vector pointing away from the black hole, which I can write as XL divided by R. Okay, and I also need to tell you what the epsilon is. It is the completely antisymmetric Levashevitov symbol. Okay, in the conformal space, so it means it just takes values of 1, 0, or -1. Okay, so this is Levy symbol. Okay. This solution describes a black hole with angular momentum JK. That is the first solution. Here's another solution. Yeah. Namely, Aij bar equals 3 divided by 2 r squared times pi lj plus pj li plus li lj minus gamma bar ij times lk pk. Okay. This is the solution for a black hole, with linear momentum pi. Okay. These solutions, basically both of them, were derived by Bowen and York in the early 80s, and so they're called Bowen-York solutions. Okay. So this is from 1980. And I think these are really beautiful. Okay? It means that they give you analytical solutions to the momentum constraint, okay, for basic vacuum solutions, so black holes that carry either linear or angular momentum. And I think you have trouble reading something, right? Is that right? You all set? Okay. Okay, good. Okay. We're all good? Okay, so again, basically, once you have the solution, of course, you can check whether there are solutions by inserting these expressions into this, remembering that these operators in Cartesian coordinates would just be partial derivatives, okay? So it's just a matter of just checking that and doing all these partial derivatives and whatnot, okay? If you're wondering how were they derived, then you follow this recipe that I suggested. You basically split this tensor into one part that has zero divergence and one that has non-zero divergence, and then you use this result that the non-zero divergence part you can write as this vector derivative of a vector, okay? And then you can find analytical solutions to that vector, similar to how you would do this in E&M. Yes? Oh, I'm sorry, this is not a minus. Is this what you're referring to? I'm sorry about that. No, this is a bar, okay? And I'm inserting the bar because I want this to be the Levi-Civita symbol, or the tensor in the conformal space, okay? Remember, basically, in general, when you write down this tensor, there will be a determinant of the metric in there, okay, to make it invariant. But that term is not there, okay, which is the case for this. So basically, it's the Levi-Civita in the conformal space. That's why I decorated it with a bar.
What does that exact term mean? That I epsilon large? What is this?
So I'm sorry. Okay, you're asking about the I and the J here? Oh, in the parentheses? Oh, I'm sorry about that. It means symmetrization. Okay, so if I'm sorry, I should have said that. I apologize. Okay, so if I write, let's say I have a tensor, ij, and when I put these two indices in parentheses, I mean symmetrization. So that is the same as 1/2 times Tij plus Tji. Okay, and there, by doing that, this automatically becomes a symmetric tensor. Okay. Yeah, I should have said that, okay? Actually, we also use, I think on Tuesday maybe, we used a similar notation with the square brackets. That is the anti-symmetrization, which would mean the same thing just with a minus, okay? Yeah, yes, thank you for asking.
So this is the full-3D solution or just some solution with some symmetries?
Sorry, it is?
Is this the full 3D solution or some solution with some symmetries?
Well, right. I mean, it's a solution to the momentum constraints, right? And basically, if you, for example, what could you do? Okay, so let's say maybe you want to say, okay, let me build initial data that describe a binary, okay, at some moment during the in-spiral. Okay, so maybe you're saying, okay, maybe at this instant, the black holes are both on the x-axis, okay? But if it's in the binary, then one should have a momentum in the, let's say, in the positive y direction and the other in the negative direction. So you could now say, okay, you could say, okay, let me place these two black holes at these two locations, but now you endow one of the black hole with a linear momentum p that is in the positive y direction, and the other black hole with a linear momentum p that goes into the negative direction. And by then using a superposition of these two, you would have solved the momentum constraint for this black hole binary, okay? So you could use that, for example, for initial data for a numerical simulation of binary in-spiral, and that is exactly what people do, okay?
So basically, all the multipolar moment information is hidden in J and K.
Sorry, so what about J and K?
All the multipolar information of multipolar moments, they're hidden in J, L, and P. Is it like
right. So, or I mean, I'm not sure I would call it multipolar information. I mean, yes, you could evaluate the multiple moments of these solutions, okay? But basically, the J and the P, they tell you about the linear momentum and the angular momentum of these solutions, right?
But by that I mean just angular dependence.
Yeah, yeah.
Dependence on angular coordinates.
Oh, so the angular dependence. Oh, right. I mean, that's hidden in these L's, right? Because the L's, these are unit vectors that point in different directions, right? Okay, makes sense? Okay. Now, mind you, of course, and this brings us to the next subject, these are only solutions to the momentum constraint. That means we're not done yet. That means because to complete our specification of the initial data, we also have to solve the Hamiltonian constraint. Okay? Make sense? So in fact, that's what we'll talk about next. We talk about, well, okay, imagine, let's say for a specific example, maybe we want to construct binary initial data, with two black holes. It's some, like a snapshot of an in-spiral. Okay, so basically at this moment, these two black holes maybe have linear momentum. Maybe they have angular momentum on top of that, so then we could add these terms if we wanted. Okay, but regardless, by having, we should celebrate this. This is amazing. So we have analytical solutions for the momentum constraint. Okay, but now we also need to solve the Hamiltonian constraint. And now let's look at what's happening here. Basically, this term will be 0, okay? Because we've chosen a maximal slice, okay? Maximal slicing. So this term is gone, but this term, of course, is not. This term we would compute by taking the contractions, or basically the square of these terms, okay? So those terms are non-zero. We would insert these terms in here, and now you notice, well, how about this term? This term is 0, okay? But then we have these two terms left. But you notice there's an issue because here's psi and there's psi to the -7. So that is now a nonlinear equation. So we have no hope to solve that analytically. So we need to solve that numerically, okay? Moreover, we could get very scared here. Because look at what's happening with these AIJs. Okay, let's take the most harmless case. Okay, the most harmless case is if we had black holes that only have a linear momentum and not angular momentum. But even in that case, if I take a square of this, as I need to do here, then I pick up a term that goes with 1/r⁴. So as we're approaching the black hole, this term diverges quite rapidly. Do we have any shot at solving this? Are there solutions? It turns out yes. And it's beautiful. Okay. And that is because this term is multiplied with psi. And remember what do we expect for the behavior of psi? If the black holes had 0 momentum, what would we expect for psi? It would be roughly like, it's 1 plus m/2r. So that means psi diverges with 1/r as r goes to infinity. That means psi, 1/psi will go with r. And psi to the -7 will go with r to the 7. Okay? And look, this is a miracle just happened. Okay? So even in the worst case scenario, when we have spinning black holes, this one goes, the square of this will go with 1/r to the 6. But now we check, and we notice that 7 is greater than 6. So basically, this term will still go to 0 as we approach r equals 0. Okay? And that is a property that is used in one particular approach, the one that I particularly like, which is the puncture method, to solve this solution numerically. So let's talk about a numerical approach for how to solving the Hamiltonian constraint given a solution to the momentum constraints. Okay, so let me, you know what? Now I will leave this on purpose because we want that equation there. So I'll erase this. Yes. You know what? Could you use a mic or something? Yeah, great. Thank you.
Yeah. So are we still holding the time symmetry for the Boyne-York solutions?
You tell me.
Because I would thought
I know that it's not fair, right? To just you ask me a question, but I will do it anyway. So what do you think?
Because there are now multiple black holes, and so they should be starting to drift towards each other, right?
Yeah.
So I would
expect. Okay, let's think about what do we mean by time symmetry? What do we set 0 to 0 for the time symmetry? Kij, the extrinsic curvature, right?
Yeah.
So, but now actually we are allowing the extrinsic curvature to be non-zero, right? because Aij is now non-zero. If Aij is non-zero, then Kij is also non-zero.
That's correct.
So that means that the answer is no, right? So basically, we're abandoning time symmetry, but there's still one part of K that is zero, and that is the trace.
Yeah.
Namely, we're assuming maximal slicing. Okay, so that means the trace of K is still zero, but the traceless parts we're now allowing to be non-zero.
So
Okay.
we also have the evolutions equations in the back.
That's right. So basically, that's
Okay.
in the back. Okay. Yeah. Okay. So let's talk about the puncture method. Okay. So this is the Hamiltonian constraint. We just discussed this. We were talking about vacuum solutions. So this term is gone. We still have maximal slicing, right? So K is zero. We're still using conformal flatness. So R bar is zero. So that means it's only these two terms left. Okay, so let's write those down. The Hamiltonian constraint is now d bar squared psi equals plus 1/8 psi to the -7 a bar ij equals 0. Okay, we just discussed that ai, the square of ai, the square of a, okay, this term diverges as r equals 0, but we already anticipate that actually the solution for psi will come to our rescue. Okay, to see that again, let's remember that in the case where aij is 0, we had psi, and now I'll call this psi 0, right? We have psi 0, that was 1 plus m divided by 2 divided by r, right? That's what you discovered already on Monday, right, in the tutorial, and we saw it earlier today when we looked at the elementary solutions to the Hamiltonian constraint. Okay, so we see that this actually diverges with 1 over r as we approach r equals 0. That means that this term will actually help regularize the divergence in here. Okay? Now we'll make an ansatz for our solution. Okay? And basically, we already know that close to r equals 0, our solution will diverge. It will be a singular solution. Here's a beautiful trick. Okay? It's always difficult to look for singular solutions numerically. So we will not do that. Instead, we will take out the singular part analytically and let the computer look for the rest, hoping that the rest will be a regular solution. Okay? So what I mean by that is this. Let's write the solution psi as the following ansatz. We write psi as 1 plus an m divided by 2r, okay, plus a correction u. Okay? And now I'll use this curly m as basically, I'll refer to that as the puncture mass. Okay? I tried to do something earlier today, right? Somebody asked me about what do these m's mean. Okay? Now I'll just call it the puncture mass. It's just a parameter for the mass. It's not necessarily the physical mass of the black hole. We would have to go back after the fact, after we're done, to analyze the solution, what actually the physical mass of the black hole would be. Okay? So, okay, this is our trial solution, our ansatz. Okay? We know that for a equals 0, this will give us analytically the correct solution. Okay? What we're now hoping is that for non-zero aij, we will get a regular solution for u that we can solve for numerically. Okay? So the trick is, and I think quite in general, this is a really great trick to keep in mind when you do numerical work. Imagine you're trying to look for a singular solution numerically, then try to get the singular part analytically, use that analytical result, and only solve numerically for the part that remains, the regular part. Okay? Okay, so now what happens in our equation, the Hamiltonian constraint, when we use this? Okay, so in order to basically just make the notation a little bit cleaner, I'll define a new function as 1 over alpha. And now careful. Make sure you catch this. This alpha is not the lapse, okay? Not the lapse. Okay, I'm just following convention. This method was developed by Brandt and Brigman, and building on some earlier work by some other people, but basically they use this notation alpha and beta, so I'll adopt that, but do not confuse it with the lapse, okay? So this is just 1 over alpha is a shorthand for m divided by 2r. What this implies that alpha itself approaches 0 as r goes to 0, okay? And now I will, yes?
When we solve for like phi naught equals to 1 plus I by 2r, we used Kij equals to 0.
That's right. Yeah.
So why have you written like a bar I equals to 0?
Sorry, what is here?
Why have you written a bar I equals to 0 there?
Oh, basically, I'm just saying for the special case, if we had black holes have 0 momentum and 0 angular momentum, in that case, Aij would be 0. And then we would just, this term would disappear, and we would rediscover the solution that we wrote down earlier, okay? And now we're trying to build on that by looking for regular corrections to this special case that takes, in other words, this correction will then account for the corrections that are due to the linear or angular momentum that these black holes carry, okay? All right, let me move back over there. So what I'll do next is I will insert our ansatz, our trial function for psi, into the Hamiltonian constraint. On the left-hand side, I have the Laplace operator acting on psi. Okay. Now, if I insert this into the Laplace operator, if I take the Laplace operator of this, you'll probably believe me the Laplace operator acting on 1 is 0, right? You also remember that was, of course, a solution to the Laplace operator. So if we act on this one, it'll also be 0, right? You buy that? So the only term that remains on the left-hand side is the Laplace operator acting on u. Okay, so let's write this down. Okay, so then Laplace operator acting on psi is the same as that operator acting on u. And on the right-hand side, if I move this term, this aij squared term to the right-hand side, okay, then I get on the right-hand side minus 1 over 8. And now psi to the minus 7, that will be 1 plus 1 over alpha plus u to the minus 7 times aij. Okay. And basically this I can pull out a factor of alpha out of this expression. Then I get 1 over 8 alpha to the 7 times aij times alpha plus 1 plus alpha u to the minus 7. Okay. Now, remember this term diverges, but not faster than r to the minus 6. This term goes with r to the 7. So this term remains regular at the puncture, what we call the puncture at r equals 0. Okay. Now, again, basically following what Bernd Brigman and Steve Brandt did, I'll call this beta. So this is not the shift. Okay. This is just a new variable. Okay. And you notice that beta approaches 0 as r goes to 0. So that means the right-hand side is now a perfectly regular expression, which we can now solve for u. Okay, so now basically we have an elliptic equation, a regular elliptic equation for u, which we can write as minus beta alpha plus 1 plus alpha u to the minus 7. Okay, notice that this beta is given completely analytically. Once we've written down the analytical Bowen-York solutions for aij, we can evaluate this analytically. The alpha is also analytical, right? Because it is just this term m divided by 2r. Okay, so this beta, basically you compute once. It's an analytical expression, and then we have these terms left. And basically, this is now it's an elliptic equation, so we can invert this operator pretty easily. Okay, even though it might be very slow, but never mind. And if this were a linear equation, you could do this in one step after inverting this operator. Okay, but since it's a nonlinear equation, you have to do it iteratively. But you can solve this equation. Actually, we'll skip some of the numerical details. You will learn about a lot of the numerical techniques next week. Okay. But the bottom line here is that this gives you regular solutions for this correction U, okay? And once we have these corrections U, from U, we can then construct the conformal factor. And once we have the conformal factor, then together with these solutions to the momentum constraint, we have completely specified the initial data, for example, for a binary black hole in spiral. Okay. Okay. Make sense? That is neat. Okay. You should be excited. Okay. That's how we can do that. Okay. By solving only one elliptic equation. Okay. Now, again, as a general idea, okay, I should tell you this. This was developed by Brand and Brickman in 1997. There's the general philosophy for numerical work that I really like. Essentially, you should always try to do as much work analytically, and only the part that you cannot do, let the computer take care of that. Okay, but any knowledge that you have analytically, you should use. Okay, in particular for singular functions. Okay? Now, basically, as part of the tutorial this afternoon, I'm actually giving you a little script, a little Python script, which is called puncture.py. That is actually a script that solves this equation. Okay? So you can actually play with that. You can look at that script and you can actually run it on your computer. It should run very easily. Okay? That is a script that is written purely for just playing around. It's certainly not like a research tool. It uses no particular tricks that allows you to invert these operators for real large runs. You want to make sure that you store all the memory for these operators very efficiently. That script doesn't do that. It's just right out of the box. Therefore, it is very slow as soon as you make the grid large, okay? Or even moderately large. But nevertheless, it allows you to play with that and actually see how all of that works. And you can, it is implemented for one particular Bone-York solution. You can see where that is entered into the script. You can modify that. You can add the other one and you can play with it, okay? So you can explore this puncture method with the script puncture.py, okay? And you can do that this afternoon. I'm also giving you a second script that allows you to basically make plots of the solution so that you can actually visualize these functions U that you get in this way, right? And that's all I have for today. I think that's pretty good timing, actually. So this is where we'll stop, unless you have any more questions about any of this. Are we all good? Then that completes our discussion of the initial data. And that what remains to be done is talking about the evolution equations, which we'll do tomorrow. Okay. All right, yes?
So,
yeah.
We make the answers for psi, which is superposition of the simple solution plus U.
Mm-hmm.
But the equation is nonlinear.
So it is the Hamiltonian constraint is nonlinear. That's right. So basically, the Hamiltonian constraint is nonlinear. So that's right. So basically, that means U will also enter nonlinearly. Okay. So in practice, how do you solve this? Okay. Basically, you linearize that equation. So basically, you say, let's say we have one iteration step. At that iteration step, we have a certain guess for U. Then you linearize this equation about that current guess. and you allow for a little change in U, maybe you call it delta U. We linearize in delta U. We bring this, so this will give us something like a -7 delta U in a Taylor expansion, okay? And so basically we do a Taylor expansion about the current gas. Then we bring this delta U to the other side, and basically we then solve for the delta U for the correction. So then we have a linear equation that we can solve for this delta U that gives us if all goes well, that gives us an improvement to the current gas. And basically for each gas, we can evaluate the residual of this equation, which tells us how close we are to having a valid solution. All right? Yeah, good. Mhm. Anything else?
For this method, so should we ignore for R is equal to zero and for every
So it's a question, should we ignore Aij equals 0? Is that what you're asking? Well, tell me what you mean by ignore. Okay. Yeah, so it basically, this particular, let me put it this way. Where did this particular Ansatz, if you like the word Ansatz, or this trial function come from? This trial function came from knowing that if I have black holes with 0 momentum, the solution is given by this, okay? So therefore, we're using this part in setting up our trial function, okay? So, but now that we have our trial function, of course, now we're saying Aij is non-zero, okay? So in that sense, you're right. Now we're ignoring the trivial solution, but we've used that information already in setting up our trial function. Did that answer your question? Yes. Yeah. Okay, great, good. Yeah. Okay. Anything else? All right, okay. Then I will see you later.